Hi, everybody, and welcome to an episode of Echo Live. My name is Anna, and today we are talking about giving physics a spin. Let's go ahead and make sure. Can everybody hear me okay? This could be a good check of our features here on Zoom. I cannot always tell at the very beginning of our programs if you can hear me. So if you can hear me, give me a thumbs up or let me know in the chat if you're able to hear me. If not, we'll switch our microphone over. I know we've had some problems with that here on Echo in the past. So go ahead, let me know. Can you hear me? Awesome. All right. It looks like we finally got this figured out with our sound system there. Happy Friday, everybody. We are talking about physics today. And specifically, we are talking about the physics behind things that spin or that rotate around in a circle. So we are talking about angular momentum. It's something we've covered here and there on Echo in the past, but today we're going to take a deep dive into angular momentum, figure out just how it works and how it applies to some things that we see in our everyday lives. Now, I thought we'd start with something kind of fun. If you've heard of the water bottle flip trick before, give me a thumbs up or give me some sort of thumbs up reaction either in YouTube, in Facebook, or here in Zoom. Let me know. Have you heard of the water bottle flip challenge? Basically, it goes something like this, right? You take a bottle full of water and you give it a spin and you try to get it to land right on its end without touching it. So you give it one good flip, it flies through the air, rotates around, and then lands right on its end. So it's a pretty popular trick, and it takes a little bit of practice. I'll admit that I am not perfect at it. I'm sure that some of you at home might be even better at the water bottle flip than I am, but there are some really interesting physics behind this trick as well. Let's start with this water bottle right here. And you'll notice that this one I have full almost all the way to the top with water. I've just dyed it with some red food coloring here so that you're able to see the water inside because that's going to be important. Watching the water or the movement of the water inside the bottle during this trick is a lot to do with the physics behind it. So let's go ahead and give our first water bottle a flip. Again, the goal, right, is to land it right on its end. Let's see. Ooh. All right, give it another try. And right, it wouldn't be Echo Live if we gave up right away. Let's give it one more good flip here. Maybe try to flip it a little more gently. And it just didn't quite work. Now, when the water bottle is full like this and it's spinning, its center of mass is largely the same the entire time. Since this water bottle is almost all the way full to the top, just a tiny little pocket of air there, when the water bottle spins, its center of mass is constant. It's not moving between the water bottle or across the water bottle. So its rate of rotation stays the same. No matter what kind of flip you give it, the speed of the water bottle once it's flying through the air is constant. It's going to keep spinning at that rate until an outside force stops it, like hitting the table. But let's give our other water bottle a try here. Now, if you've given the water bottle trick challenge a try before and you've been successful at it, you'll know that the key to the water bottle flip challenge is that your water bottle should only be full about a third to a quarter of the way full with water. The rest of it should be air. So let's go ahead and give that a try. And would you look at that? First try, I truly had no idea that was going to work out so well for me this way. But you'll notice that it was much easier. And if we could take a slow motion look at this water bottle while it's flying through the air, even though I'm throwing it with the same amount of force as my full water bottle, it actually starts at one rate. So it starts spinning pretty quickly. And then once the water bottle gets into the air, watch carefully, the water bottle actually starts to slow down. Take a look. Now, if we could get a slow motion video of this, you'd be able to tell much more easily, but I always come prepared. So I do have a diagram for us. We said the key to this, right, is that the water inside this bottle is able to move. It's actually able to change its moment of inertia by changing its center of mass. Let's take a look at a picture of what this water bottle might look like if it were flying through the air, right? So we can see that as the water bottle moves, our water starts to travel across the water bottle. So it starts centered or in the very bottom, right? Because it's being pulled down to the bottom of the bottle by gravity. But as we flip it through the air, the water starts to spread out. Its center of mass begins to change. With this change in mass, or its change of radius, we actually get a increased moment of inertia, which is a big phrase, but basically that's going to result in a decrease in speed or velocity. We've talked about this once before in the past, that this angular momentum, or this moment of inertia, is easiest to understand if we think about it like a spinning figure skater. So if you've ever seen a figure skater, right, you notice that when they're spinning, they will start to pull their arms in towards their body, which will actually increase their speed, right? They start to spin faster as their arms get closer to their body. If they bring their arms out, they start to slow down. Let's take a look at that in a GIF. We've taken a look at this GIF once in the past here on Echo. This is a super slowed down version, but we can see that when the figure skater pulls her arms in, her velocity or her speed increases. Angular momentum is something that has to be constant within a system. It never changes unless it's acted on by an outside force from outside the system. In this diagram, right, the Fidget Spinners are the figure skater's arms are part of her own system, but she can change a few things just by changing her center of mass. Now, we say that angular momentum is the product of two things. It is the product of your speed or your velocity, so how fast she is spinning, and her moment of inertia, which is basically, in very simple terms, it's her radius. It's how far the mass is from the center of that rotation. So if angular momentum is a product of those two things, if we increase one, we have to decrease the other in order to keep angular momentum constant. So let's take a look at that. You'll notice my studio is set up a little differently than normal today because I want us to be able to take a look at this thing down here on the floor. So down here on the floor, if you've ever wondered what the floor of the distance learning studio looks like, here you go. It's a little messy, but I have a rotating platform, which is going to allow us to simulate those same physics of that figure skater, right? I'm going to stand up on our rotating platform here. You'll notice that I can kind of rotate my body around, especially if I give myself a small little push off our table here. But this would work better, right, if I could increase my moment of inertia using some weight, right? So I've got some just little hand weights here. They're 3 pounds each, right? And that is going to help to increase my moment of inertia, the amount of mass or the distance of the mass away from the center of my rotation. Now, let's take a look at what happens, right? The two things we're looking at are our moment of inertia, this distance here, or our velocity, the speed at which I'm going to spin. So I'm going to start myself off backwards, actually. So I'm going to start my spin off, and then let's take a look at what happens when I bring my arms in and away from my body. Ta-da! We saw that when I pulled my arms in, right, as I decreased that moment of inertia, we had to see an increase in velocity in order to keep my angular momentum constant. Let's try that one more time. But once I put my arms back out, almost immediately, right, that increase in my moment of inertia by putting my arms way out wide caused a major decrease in my velocity or in my speed. Someone said faster, and so we'll try this one more time. So these were 3-pound weights. Let's go ahead and give it a try with some 5-pound weights. These are very, very heavy. I don't like to use them because I'm not very strong, but let's go ahead and give that a try, right? Because our moment of inertia is a product of the amount of mass and the distance away from the center of rotation. So let's give that a try one more time. Start off towards the back, just like we did last time. And here we go. All right. That's a little bit, that's one way that angular momentum has to do with a change in the system, right? We can see a change in the speed based on our moment of inertia just by manipulating the mass That was the same thing that allowed our quarter full water bottle to be much better at our water bottle flip than the all the way full one, because the center of mass, or the moment of inertia, in this full bottle is constant. There's no change, and so there's no change in the velocity while it's spinning through the air as well. But we can also think about this spinning force in terms of the force and the direction. So let's take a look at another picture here. All right, now it wouldn't be Echo Live, right, without another right-hand rule. This right-hand rule is really, really easy to understand. When we think about something that is spinning, it has a direction of rotation. In this right-hand rule, the direction of rotation is going to be simulated by curling your fingers in that same direction. So we can see that in this diagram, right, our direction of rotation, if you could imagine this was a bike wheel or me spinning on the spinning platform, right? This is the direction of our rotation. You would curl your fingers in that same direction so that your fingers are pointing the same direction as the arrow. And then your thumb is what would give us the direction of the force, or what in this case we might call the torque. Now, this is the same thing that keeps our bicycles balanced. So we've got another picture first, but let's just go ahead and show you something to begin with. I have here in the studio a small bike wheel, right? And if you were riding your bike, right, you'll know that for the most part, your bike will actually keep itself upright. You don't have to do a lot of balancing once the bike wheel is really, really moving. This has a lot to do with torque. So if I take my lanyard here and just go ahead and clip it onto the end of the handle here, so I've got it clipped to the end, tell me in the chat, if I let go with this hand, if I let go with that hand right there, what is going to happen to my bike wheel? What will happen if I let go with this hand? Tell me in the chat. Make a hypothesis using your knowledge of what we've learned about forces on the past in Echo Live, or maybe what you might know, right? So the bike wheel is not spinning. It is completely stationary. What's going to happen if I let go with this hand that I'm wiggling my fingers on? What's going to happen to the bike wheel? Go ahead, tell me in the chat. Good job, everybody. You guys are so smart. We know that the force of gravity, right, is going to cause the bike wheel to fall or to turn towards the ground, right? So the bike is connected here by my lanyard. And so gravity is going to pull the mass of the bike wheel down towards the ground as soon as I let it go with this hand, right? But if we think about our right hand rule, if we get the bike wheel spinning, so remember you have to use your right hand for this rule. If I get the bike wheel spinning in this forward direction, so towards you at home, I'm going to start to spin the bike wheel very, very quickly. That will result in a force in that direction. So in the direction of my thumb. So remember, the curl of your fingers represents the direction of the turn, and my thumb is the direction of the torque, or the force on the system. So let's go ahead and get my hand nice and ready here. Let's go ahead and get our bike wheel spinning. And this bike wheel, you'll notice, isn't going to work very well, but I have a better one. So this is great to talk about that angle, or that moment of inertia. Now, this bike wheel is much heavier. It's much heavier, and the radius is much greater. And so the moment of inertia on this bike wheel is much better. And it's actually much better for this demonstration. So let's go ahead and give that another try. All right, so again, we're turning the bike wheel towards you, right? So if I were to use my right hand towards you, curl my fingers, the force goes towards my table. Get everything set up one more time here. All right, perfect. Get our bike wheel started spinning in your direction, and take a look at this. Oh, a little faster. Does the bike wheel fall right down? It doesn't, right? That torque that's being exerted on our bike wheel is actually greater. The direction of that force is actually greater than the force of gravity. Therefore, my bike wheel doesn't fall towards the ground. I can try this one more time. I think I'm getting a little caught up on the direction here. which isn't super important, right? Whether I turn the bike wheel this way and the direction is back towards the wall, or if I turn this way and the torque or the speed of direction of the wheel, right, goes towards you, doesn't truly matter as long as our rotational motion exerts a torque that's greater than the force of gravity. So in this case, go ahead and see. Our bike wheel is defying the force of gravity, right? But over time, right, friction is going to slow down the rotation of this bike wheel. And eventually, our bike wheel, the torque that's being exerted on the bike wheel or from the bike wheel will become less than the force of gravity. You can see that it's slowly starting to tilt towards the ground, slowly, 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 until eventually gravity will be the greater force. Now, if there was no friction in this bike wheel, if this had really, really nice ball bearings, this force could last much, much longer. But let's think about how this works in terms of steering, because we said that these forces come into play in our daily lives. And I'm sure that most of us have either learned or are learning how to drive or ride a bicycle. All right, when we're riding our bicycle, right, we said that that torque, that direction L, which is represented as L in this diagram, is greater than the force of gravity, which keeps our bike upright as our tire is rolling forward. So go ahead and try to find the direction of the tire's rotation, right? If the resulting force is L, you have to use your right hand. You can't use your left hand. So hold up your right hand, point your thumb in the direction of L, and then think about, right, our tire must be turning forward, which would mean this bike is going forward. But because of this resulting force, right, any change on the system will give us an equal and opposite change in the system back. So if you were to lean over to the side, not even to turn your bike wheel, if you were to just lean to the side, right, we would have a change in the resulting force. Now your force or your rotational motion, right, is over this way. And so if you turn your hand, go ahead and try this. So normally we said that our tire is turning forward and our resulting torque is that way, the direction of my thumb. But if you start to lean your bike, right, we have to turn our hand, to rotate our fingers over, and the resulting torque is actually back towards the wall, which would cause my bike to turn, even if I didn't turn my handlebars, just leaning to the left and that resulting rotational motion. So if you rotate with your thumb, the torque will turn your bicycle. And this process we also call gyroscopic precession, and it's how we steer helicopters. So helicopters, right, don't have handlebars, and they certainly don't have a steering wheel where we can turn the tires, right? It's all about the movement of air and the resulting force on the system, right? So we turn helicopters by the same gyroscopic precession that you would use by either leaning to the left or to the right on your bicycle. We can use our giant bike wheel to show you exactly how this works. Go ahead and turn our camera back over just a little bit. All right, now in this system, right, the bike wheel, myself, and the platform, we are all part of one system. And as long as there's no outside force to change it, we won't see any resulting change in force. I should just continue standing exactly where I am. But I'm going to get the bike wheel spinning, and then let's take a look at what happens. All right, so I'm going to turn the bike wheel now. And you'll notice that there's a resulting force on my body. It's actually spinning me around very, very quickly. This is exactly how we steer helicopters. You can think of this rotating blade just like the rotating blades on a helicopter. They do spin around in one constant direction. And if helicopters want to go right or left, instead of turning the bike wheel right or left, right, we have to think about it in terms of the right-hand rule. So once the blades are spinning, make sure we get it spinning nice and good. I'm gonna put my foot flat on the ground so I'm not on the rotating platform while I do this. If I now turn the bike wheel forward or backwards, there's a resulting force on my system. And it's actually a very, very strong force. So helicopters won't actually turn right or left. They actually tilt forward or backwards in order to get themselves to go right or left. So think about that in terms of your bike. And if you're ever curious about it, right, remember that it's all about that right hand rule. All right, now most people don't have a spare bike tire laying around their house. I'll tell you, it's really, really heavy, and it's made my arms really, really sore from playing with that all day here in the studio. But what you might have laying around home is something called a fidget spinner. I haven't seen a fidget spinner around lately, but fidget spinners work off of that exact same physics. And this is an activity that you can try at home. If you don't have a fidget spinner, you can actually make your own using just a couple really simple materials. We have this activity posted on the Michigan Science Center's website. This was part of an activity we did with Metro Parent Magazine. We taught people how to make their own fidget spinner so that you can practice feeling the right hand rule right inside your hands. You only need a couple things for this experiment. I've made one ahead of the program right here. They work really, really well. So you really just need some scrap cardboard. I've saved the box from my waffles that I finished. You'll need a template, which came right off of this activity guide, which you can find on our website. You'll need a push pin. You're going to have to stab through the cardboard with this push pin. So if you're not comfortable doing that on your own, get an adult to help you. They'd be more than happy to. You can teach them the physics behind this experiment as their reward for being such helpful assistants. You'll also need a couple pennies. So I've got 3 pennies here and a toothpick. All right, so there's a really simple set of instructions that go along with this. You're basically going to trace your template and cut out some of those pieces from the template from your cardboard. That's going to give it just a little bit more shape. I've then glued my pennies to the outside here, right? Because the pennies are what's going to give this fidget spinner mass or increase its moment of inertia while it's spinning. We want the mass to be away from the center, right? And then I've just taken my toothpick and I've poked it right through the center of my fidget spinner here and glued it all together. And then you actually get a toy that demonstrates those same principles of angular momentum. As you turn this in your hand, or if you've ever turned a fidget spinner before, the satisfying part about them is that you can actually feel that force, that conservation of angular momentum right inside your own fingers. So if you have a fidget spinner, you don't necessarily need to make your own using our activity guide. You can pick it up, and right after Echo today, you can actually feel that angular momentum, that change in the system or the force when you turn your fidget spinner in any direction. This is a great way for you to practice using that right hand rule as well, right? So think about it in terms of which direction you are turning it. And remember that your fingers on your right hand will represent the direction of that turn. And then see if the direction of the force you feel on your hand matches up, because your thumb will represent that force. So fingers are the direction and thumb is the force, the resulting torque. So it's a really cool activity. Again, this is one of those activities that's listed on the Michigan Science Center's website. You can find that if you go to our page and you look for At Home Science. The website is listed right here on the very bottom. As always, we are very, very thankful to our sponsors like Ford and Denso, who allow us to bring these programs to you at home every single weekday at 2:30 p.m. But I do have a special note on this slide that there actually will not be any Echo Live this coming Monday. This weekend is the holiday weekend. I know that lots of people have Memorial Day plans. The Michigan Science Center is going to be observing Memorial Day, and so we are not going to have an episode of Echo Live on Monday, but Tuesday, May 26th, is actually going to be Echo Live's 50th episode. That's an amazing milestone for us. We are so excited that so many people have tuned in from the very first day of Echo Live. You've been with us for 49 episodes. I hope you've learned a lot. And so I figure on Tuesday, we can have a big shebang. We can do some really, really fun, large-scale, exciting science experiments to celebrate our 50th episode. You won't want to miss it. It's going to be an amazing time. Don't worry, I will miss you on Monday, but we will be back on Tuesday with one of the best episodes we've done so far. with that, I hope that you all have a great weekend. I hope that you have an amazing time. If you have any questions about the program that we've taught so far today, feel free to send them in the chat. We have a few minutes left to answer them. If you have any questions or maybe guesses about what we might talk about on Tuesday for our last episode, or for our 50th episode, not our last episode, don't worry, of Echo Live, type those in the chat as well. I'd love to see what you guys think we might be talking about, or maybe some suggestions would be really cool as well. If you have questions, type them in the chat. I'd love to answer a few if we've got them. A couple people really excited. I see a couple friends who I've seen here every single episode of Echo Live, and it makes me so happy that everyone is enjoying these episodes, that you are liking them, that you're sharing them, that you're trying some of our activities at home. I hope that you do, because this has been one of my favorite experiences at the Michigan Science Center so far, is talking to you all every day, hearing that you love science just as much as I do. It is so rewarding to me, and I'm so excited that we'll see you for a whole lot more episodes of Echo Live before we wrap up. With that, it doesn't seem like we have any questions coming in just yet. I'll stay around for a little bit longer, just in case. Let me scroll through our comments here. I know we've got friends watching on all sorts of platforms. No questions on YouTube. A couple people telling us, oh, that you, Brenda, tried our lava lamp experiment at home. That is so awesome. I'm so thrilled that you guys are trying these things at home. You can find all of those activities, of course, on the Michigan Science Center's website. This is our at-home science activity page. Here's the link to our fidget spinner activity that we just talked about. We did pen chromatography earlier this week. We've got all sorts of stuff on this. So if you're looking to do something science related this weekend, maybe you're missing out on Monday's episode of Echo Live, don't worry, we've got lots of stuff on here. Try them out, tag us if you do, so that we can see that you guys are engaging in STEM at home. It makes us so happy to see that. A couple people, I will say, we've got a couple people making suggestions for videos they'd like to see. I would love to talk about crystals. We do have one crystal growing activity on that at-home science page, but we can certainly talk about crystals on an episode of Echo Live. You got to give me a few days to get things prepared, because if you do know anything about crystals, they take a little bit of time. In nature, they form over hundreds of years, but I think I can come up with something just a little bit quicker than that, and maybe make it so that you can all grow crystals at home as well. So with that, thank you everyone so much for joining us for another episode of Echo Live. I hope you have a fantastic and a very safe weekend at home. Enjoy your Memorial Day holiday, and then I will see you back here on Tuesday for our 50th episode celebration. Bye, everybody.